Okay, guys, so here's what we're up to today. And these are two separate things. We are going to talk for about 11 seconds about polyprotic acids. You just simply need to know what they are and understand a little bit about their chemistry, but literally it's going to take us no time at all. Then, guys, the brunt of what we're going to talk today about will be about the pH of salt solutions. This is good chemistry. This is fascinating. So this is where we're going to spend most of our time. The table that I gave you is actually a synopsis of what we are going to talk about with the pH of salt solutions, and we will end today by actually solving kind of a thought-provoking problem. But before we do, we got to do polyprotic acids because frankly it doesn't fit anywhere else, and eventually we got to talk about it. So here we go. So guys, when we talk about polyprotic acids, what does poly mean? Many. Protic refers to protons, so we're talking about acids with many protons. So this is what we're talking about. Guys, polyprotic acids are acids with more than one, and I'm pretty sure I made this word up, protonatable. I like it. Protonatable protons. So guys, let me show you what I'm not talking about. And you may want to write this down as a negative example. So when we look at acetic acid, that is not polyprotic. But now you're going, wait, it's got a bunch of hydrogens. But guys, only one of those hydrogens can come off. If you draw its Lewis dot structure, it actually looks like this. And which one of those is the protonatable hydrogen? The dude on the right. So guys, why can't those other hydrogens come off? We're going to talk about that Wednesday. Because guys, not only does the conversation talk about that, but guys, what about this? This has got OH in it. Why doesn't it act as a base? Why is it that acetic acid is a monoprotic acid and not a polyprotic acid and not a base? And it gets even better. Why isn't this an alcohol? Because guys, alcohols contain OH as well. That's everything that we're going to talk about on Wednesday. But this is not a polyprotic acid. So what is a polyprotic acid? Well, guys, consider this. Sulfurous acid. Yeah, not sulfuric. This is sulfurous. So guys, this is what sulfurous acid does. It gives away a hydrogen. You may want to write this down with me. So guys, sulfurous acid as an acid gives away a hydrogen. But notice the way, well, we should talk. Why the double-headed arrow? Well, because it's not a strong acid, right? Sulfurous acid is not one of the big seven. It is not a strong acid. It is a weak acid, therefore it reaches equilibrium. And so when we talk about weak acids, we can then talk about Ka values. Guys, notice the Ka value of this acid. Yeah, good. I was wanting to bring that up next. Guys, this is a pretty big Ka value. It's on the order of 10 to the negative second. If we were iceboxing this, it would not be appropriate to disregard the minus X because this acid breaks apart actually fairly extensively. The thing that is interesting then, and the thing that's new to the chemistry that we've been talking about, actually then becomes this. Guys, what does this do? Well, we understand that this is a conjugate base, right? Is it a worthless conjugate base? It is not. It's actually a fairly good conjugate. Well, we should be careful. So is it a worthless conjugate base? No, because that would make it a strong acid, right? But guys, this is a fairly strong weak acid. So what do you know about the ability of that to function as a conjugate base? Not very good. What is its Kb value in general? 10 to the negative 9th to 10th, right? Because Kw is Ka times Kb, and if Ka is 10 to the negative 2nd, then Kb is going to be on the order of 10 to the negative 10th. So this is not a very good conjugate base. But guess what? It is a pretty good acid. And so guys, what this will do is this HSO3, this bisulfite ion, will actually give away another hydrogen.
We talked about this in our first acid, didn't we?
A long time ago. And now we're coming back to it. Yep. And guys, obviously, once the HSO3, which is called bisulfite, once bisulfite loses that second hydrogen, then it's done. In just a second, tell me. But this is the thing and I'll ask it as a question rather than say it as a statement. What do you think the Ka, what will the Ka of HSO3 be compared to the Ka of H2SO3? Will it be a better or a worse weak acid? It'll be worse. Why? It's charged, right? It lost a hydrogen, it's got a charge. That charge, that negative charge, makes it more likely to hang on to its hydrogens. So it is not as effective of a weak acid as the original acid. And so as we would predict, its Ka value is actually 1,000,000 times smaller. The Ka value of this is on the order of 10 to the negative 8th. So it is a lot smaller. But it is still an acid. It is still a weak acid. It's not as good of a weak acid, but it is still a weak acid. Yeah, so its conjugate base value is actually increasing. So the basic strength, if you will, of the sulfide ion would be 1,000,000 times stronger than the basic strength of the bisulfite ion.
Is it just the 1,000,000 in this case? Or is it
No, it's just in this case. Yeah, so tell me what, but understand this does always get weaker.
Yeah.
But it's not always 1,000,000. Tell me you had a thought.
So the Ka1 value,
Yeah.
that does not include the Ka2.
That's correct. That's right. And guys, that's what we need to talk about today. How do we deal with the strengths of these weak acids when they're giving away multiple protons? And the answer is this. So we understand that the Ka for the first ionization is always higher. But when we're trying to figure out pHs for these things, this is what we're going to do. So long as the Ka value for the successive protonations is at least 1,000 times weaker, then we can find the pH of the acid by only dealing with the first protonation. I know you want to write down the words.
Trying to interpret the words.
Yeah, and that's good. Well, yeah, but we understand it's weaker, so I didn't feel like I needed to include the negative. It's 1,000 times weaker. So guys, I know that you like to write things down carefully, so I'll let you do that, and then we'll explain it, and it'll make sense. Just let people catch up. People are drowning in the words right now. You guys okay? Y'all caught up? So let me take a swing at explaining this, and then we'll do questions. So guys, there's a principle, and then we can talk about the math. So the principle goes like this. We've got two substances here that are functioning as acids. The second is the child of the first. And we know the Ka of this, and we understand that that's relatively strong. But then we come down here to the Ka of the second, and we find out that it's 1,000,000 times weaker. So if we wanted to find the pH, so if we had a 0.1 molar H2SO3 solution, and we wanted to find the pH of the solution, what would we do? Well, guys, the first thing that we've got to do is we've got to figure out, do we need to include the hydrogen ion that is being created by the second protonation? And guys, that's what this is speaking to. So the idea is this. If this Ka value, the second Ka, is at least 1,000 times smaller than the first Ka, then you can disregard that. The amount of hydrogen that's given off in that second step, because the second step has a Ka that's more than 1,000 times smaller, the amount of hydrogen that's given off there is insignificant compared to the amount of hydrogen that's given off there, and that means we can just disregard that second protonation. Now guys, what if this had been 10 to the negative fourth? Then you can't disregard it. And so we'll talk about how to handle that in a minute. But so long as that's 1,000 times smaller, you're okay to disregard. Then the question becomes, how would we figure out the pH of this? So if we wanted to figure out the pH of a 0.1 molar H2SO3 solution, what would we do? Well, we'd icebox this, right? Just like the homework that you graded, we'd icebox this, we'd solve for the hydrogen ion concentration and take the negative log of it. Now, what if this second step had a P or a Ka on the value of 10 to the negative fourth? Well, then we couldn't disregard it, and what we'd have to do is we would have to icebox this as well, and then we would add the molarities together, and then we would take the negative log of that. Does that make sense? So that's what we're getting at. Go ahead, tell me.
So when HSO3, since that's the conjugate base,
This guy?
yeah,
Okay.
specifically the one on the top.
Okay.
So when it goes in the reverse reaction,
Yes.
is it also acting a base by
Yes.
taking hydrogens away from oxygen, or does it always take the hydrogens away from hydrogen?
It always takes hydrogens away from hydronium. The reason is because hydronium ion is a better acid than water. So the thing that will lose the hydrogens is always the thing that loses the hydrogens more easily, and that would be the hydronium ion.
So it's never going to create the wave.
Well, be careful with never, but we don't treat it as if it does. We always think of it moving, because you're right, that this is technically this, right? And so we understand, or the predominant chemistry that takes place is the removal of hydrogens from hydronium. So, I mean, there is the possibility that they could bump and water could give away a hydrogen, but it happens so infrequently we don't think of it as the chemistry. Yeah? Oh, I hope not, because that would get hideous. No, you can't, because you don't know the Ka. You couldn't attribute for both Kas, so that wouldn't work. Yeah, you guys good on polyprotics? Is this okay? All right, so guys, now let's get into, and this is interesting, but really let's get into the meat of what we're doing today. It's the video. I know. So, guys, I firmly believe that you can teach a very solid chemistry, a college chemistry course, by simply watching this video every day and talking about it in so many different contexts. So, guys, let me show you the context that we're going to talk about this now. You might draw a little line in your notes. Or segregate your notes, because now we're going to talk about something completely new. It's not polyprotics. Guys, we are now going to talk about the pH of salt solutions. That's why we're going to watch the video. Oh no, this video, no. Forever and ever, amen. All right, so guys, you may want to write these things down with me. So let's consider HCl. And I'm going to include the water. When HCl goes into water to form an acid, it does this. Would you guys buy that? We okay? Do I have the right arrow? That's the right arrow? Why is that the right arrow? Guys, okay, yeah, but why?
Because it ionizes completely.
Why? Because chloride ion is worthless. All right. Now, guys, let's do this. Sodium hydroxide is a base. Well, I was considering putting this in water. It is in water, but we're going to talk about it without the water. So, guys, do I have the right arrow? I do. And so now, guys, as we think about this, this is actually our conjugate acid. Does it go the other direction? It does not. So what do we know about sodium ion's ability to act as a conjugate acid? It's also worthless. Okay? Now, guys, do this. So maybe we should, here, let me get rid of Ca. So let's do this. So this is a worthless conjugate acid. This is a worthless conjugate base. Now, guys, do this. CH3, and I know you're sick of vinegar, but that's all right. I'll include the water. And that should be plus water. Well, all right, plus water. Do I have the right arrow on this one? I do. And again, the idea is why. And don't say because it's a weak acid. Why is acetic acid a weak acid? Because it's all about this. Because the conjugate base does function as a base, and it drives the reaction to equilibrium. Do you get the idea? You okay? Okay, so chloride cannot undo the reaction. Chloride has absolutely no ability to distill hydrogens from water. It doesn't do that. This does this. This is a base. It's not a worthless base. This is a weak base. And it can steal some of the hydrogens from hydronium and push the reaction in the other direction. Does that make sense? Okay, guys, so let me now tee up for you what we're going to do today. You ready? Check this out. We're going to take sodium and we're going to react it with chlorine, and we got sodium chloride. When this dissolves in water, and I will show you the video, when this dissolves in water, what happens to the sodiums and the chlorides? They separate. And then what surrounds them? Water molecules. And what do the sodiums and the chlorines do to the water molecules? Nothing. Check it out. What do you know about chloride's ability to act as a base? It's worthless. It does not do anything to the water. What do you know about sodium's ability to act as an acid? It's worthless. It does nothing to the water. But guys, what about this? What if we take sodium acetate, which is also a salt? What if we take sodium acetate and dump it in water? What do the sodiums and the acetates do? They separate, and then they get surrounded by water molecules. What does the sodium do to water? Nothing. It is a worthless conjugate acid. But guys, what does acetate do to water? It acts as a base. And so guys, what happens is this. The acetate ion, and I'm going to switch colors again, the acetate ion, when it goes into water, acts as a base. And it doesn't just dissolve, it attacks the water molecules that are carrying it off into solution. And when that acts as a base, this is the big idea today, guys. When this acts as a base, if this is the base, what's it going to do to water? What do bases do? Takes in hydrogens. So when that acts as a base, it's going to make CH3COOH, and it's going to make hydroxide ion. And will that solution be acidic or basic? It's basic. Guys, I just introduced you to the chemistry that you're going to learn today, and some of you are so distracted you don't even understand that you just missed something really important. If you're screwing around on your phones, put them in your pockets, focus. So guys, let's talk. So the idea is this. I just gave you two scenarios. We talked about adding table salt to water. We understand that table salt breaks into sodiums and chlorines. We established here that chloride is a worthless base and sodium is a worthless acid, and as a result, neither the sodium nor the chlorine does anything to water, and it just dissolves. But then, guys, we talked about another salt, sodium acetate. We have already established that sodium does nothing to water. But guys, down here we established that acetate ion is not a worthless base. It actually is a basic ion. So when acetate ion dissolves in water, the acetate ions actually attack the water molecules that are carrying them off into solution. When they do, the acetate ion steals a hydrogen from water. And when the acetate ion steals a hydrogen from water, it makes acetic acid, and a hydroxide ion is also produced. And now we have an excess of hydroxide ion, which makes this a basic solution. So guys, the idea then is this. When you put table salt in water, the pH remains 7, because neither the sodium nor the chlorine attacks the water. But when you put sodium acetate salt into water, the pH goes up, because the acetate ion attacks the water as a conjugate base, steals the hydrogens away from the water, releasing OH, making the solution basic and making the pH go up. Yeah?
Okay, so the weak base, the CH3COOH.
The acetate ion. Uh-huh.
We said that does has very little K value.
But we're not talking about it as an acid, we're talking about it as a base. Right? So we know that the Ka of acetic acid is 1.8 times 10 to the negative fifth. So we would then know that the Kb of this is somewhere on the order of 10 to the negative ninth. So it's small, but it's not worthless. So it doesn't do this extensively, but it does do this.
Yeah, just a little bit, because we were talking about like how much it like ionizes in the water.
Mm-hmm.
So wouldn't the NaCOOH not, would there be more of that than the acetate? So wouldn't it be?
No. Don't confuse soluble with ionized. So this will all dissolve. This will all ionize. So when sodium acetate is a very strong electrolyte. So when sodium acetate goes into water, it completely dissociates. Then some of these acetate ions, not very many, but some of these acetate ions will function as a base and pull hydrogens away from water and make a little bit of hydroxide. Not very much, because the Kb is small, right? But some of these will steal hydrogens and make a little bit of hydroxide, so it will be slightly basic. The salt completely dissociates, and then some of the acetates do attack water. Go ahead.
So after it has stolen a photon from water,
Uh-huh.
then it's acidic.
It's acetic acid.
Does it then create its equilibrium?
It does, and that's exactly what happens. So when we put sodium acetate in water, we get sodium ions and we get acetate ions, right? And guys, you okay with the idea that this happens completely? Sodium acetate is a strong electrolyte. So guys, what does the sodium do to water? Nothing. So what does the acetate do to water? Well, the acetate functions as a base and it creates this equilibrium. So if we want to know the pH of a sodium acetate solution, we have to icebox this chemistry because it is forming acetic acid. So now the conjugate acid is acetic acid, which then reaches equilibrium with the acetate ion. Does that make sense? You guys okay? So guys, let me show this to you visually if this is sort of mind-boggling. You ready? Here it comes. Wait for it. Oh. Oh gosh. Oh, I'm drawing dots. Here we go.
When an ionic
Doesn't it just feel right?
substance such as sodium chloride is placed in water, water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become separated in solution. Notice that water molecules
Okay, so guys, let's stop right here. Let's grab a pen that'll show up on here and let's talk. So this is what it looks like when sodium and chloride dissolve in water. So what do the chloride ions do to water? Nothing. How do we know that the chloride ions don't do anything to water? Well, guys, where does chloride come from? Well, we can think of chloride as coming from the strong acid, hydrochloric acid. And why is hydrochloric acid a strong acid? Because chloride is a worthless base. And so if we can establish that chloride is a worthless base, then chloride is still a worthless base towards water, and chloride will not do chemistry with water. So now what about the sodium? Well, guys, what does sodium do to water? Nothing. How do we know? Well, we can track the existence of sodium back to sodium hydroxide. And why is sodium hydroxide a strong base? Because this reaction does not go the other direction. Sodium is a worthless conjugate acid, and so consequently, sodium ion does not attack the water, and there's no chemistry going on there either. But now, guys, what about this? And this could get a little messy, but bear with me. Imagine now that our ion here is now acetate. Well, guys, if our ion is acetate, we know that acetate comes from acetic acid. And acetate actually can function as a base. And if acetate functions as a base right here, it also functions as a base right there, and it will steal a hydrogen from water and release hydroxide. Brandon, head up. You got it? So guys, what about over here? Well, what's an example of this? Well, guys, imagine that this were ammonium ion. Where does ammonium come from? Well, guys, ammonium comes from NH3. If you've got NH3 and if you've got water, you end up with ammonium ion and you end up with hydroxide. Now, what's wrong with what I wrote? It's equilibrium. It goes both ways. So what do we now know about ammonium ion? Well, ammonium ion has the ability to function as a conjugate acid, giving hydrogens away to hydroxide and forming water. So if ammonium ion can give away hydrogens to hydroxide, it can also give away a hydrogen to water and turn it into NH3, functioning as a conjugate acid. So guys, say for example, our salt was ammonium chloride. Well, if our salt was ammonium chloride, will chloride mess around with water? No, we've already established that chloride is a worthless base, so chloride will not mess around with the water, but will ammonium mess around with the water? It will, and what ammonium will do, the NH4 will actually give away hydrogens to the water, and it will form NH3, and it will form water, and that will, it'll form H3O, and that will be a slightly acidic solution. So if we put ammonium chloride in water, that will be an acidic solution because the chloride doesn't mess around with the water, and the ammonium does by giving away hydrogens. Do you get the idea? So where is this going to get truly ugly? What if your salt was ammonium acetate? Then the ammonium is going to attack the water, and the acetate will attack the water. And which one will be better? Depends on their Ka and Kb values. Are you starting to see the chemistry? You guys understand, I don't expect you to understand this yet deeply, but do you understand where this is headed? That some ions, like chloride and sodium, do not attack water. And how do we know those ions don't attack water? Because we think of them as coming from strong acids and bases. And the thing that makes them strong is the fact that they're worthless and going the other direction. Then, guys, we've got other ions that come from weak acids and bases, and their conjugates are functional as conjugates, which means that they will then attack water and function as acids and bases. That's the chemistry we're going to talk about today. Do you understand sort of the underpinnings? Then, guys, let's pull this all together. Join me over here. Write this down. So, guys, fundamentally, this is the idea. We can understand salts as being ionically bonded substances that can relate back to acid-base reactions. So guys, an example would of course be something like this. You take hydrochloric acid, you take sodium hydroxide. They're going to make salt water. But in this case, our salt is NaCl. So we think about it like this. The metal has a basic parent, sodium hydroxide. The nonmetal has an acidic parent, HCl. And so then, guys, the logic simply goes like this. When we dissolve sodium chloride in water, will sodium mess around with the water? No. How do we know? Because its basic parent is strong. Then we look at chloride. Will chloride mess around with water? No. How do we know? Because its acidic parent is strong. So when you're trying to figure out if these ions will attack the water that they're dissolving into, you need to think about who their parents are. So add hydroxide to the metal. If it's strong, then it's worthless. Add hydrogen to the nonmetal. If that's a strong acid, then that thing's worthless. That's the way to track this backwards. Does that make sense? Is that okay? It could. It really could. But you know what? We're not very politically correct. So guys, these then are the general rules. Goes like this. So if we're talking about anions, the negative ones, those are the children of the acids. Guys, if we're talking about anions, the rules go like this. Anions that come from strong acids don't affect pH. We've said that like 11 times. So examples, we understand that these things are worthless bases. Of course, the examples would be chloride, bromide, iodide, ClO3, ClO4, NO3, and HSO4 minus. Why those 7? Because those are the strong acids. But guys, what about the negative ions that don't come from strong acids? Well, the anions that come from weak acids weak acids, will react with the water. Those conjugate bases, those anions, will react with the water. And when they do, they will pull off hydrogens and make hydroxides, kind of like this. Fluoride ion. Fluoride ion is not, HF is not a strong acid, so fluoride ion will attack the water and it will produce hydroxide, so that will be a basic solution. So now what about the cations? So guys, the rules with the cations are similar. If you have a cation that comes from a strong base, those don't affect pH. So which ones are those? Sodium, potassium, lithium. What am I forgetting? Sodium, potassium, lithium, rubidium, cesium. Is that CS? Yep. Then calcium, strontium, and barium. Is that right? So guys, those are they. Those are the anions that don't attack water. How do we know those are the anions that don't attack water? They make the strong bases. Or did I say anions? Sorry, cations. Yeah, they're positive. So guys, all of those ions are worthless conjugate acids. And again, they don't attack water. And remember, we'll use the word negligible. So what about all the other cations? Well, guys, all these other cations come from weak bases. And as a result, they do attack water. For example, copper hydroxide. Copper hydroxide is not a strong base. As a result, copper ion does attack water. And when it does, it steals a hydroxide, producing hydrogen. And that would be an acidic solution. So if you were to put copper chloride into water, it would make it acidic. And green. Yes, good. That's Rachel. That's the idea. And that's the way you play this in your head. You're like, okay, so if I had copper chloride and I dumped that in water, it's all about lineage. Where does chloride come from? HCl. Is HCl strong? Yes. That makes this negligible as a base. Where does copper come from? Copper hydroxide. Is copper hydroxide a strong base? No. So now you know that copper ion does react towards water, and what's it going to do to water? Well, copper's plus, it'll take off an OH, so it'll make CuOH, and then it'll also make hydrogen ion. That would make it acidic. It's a spectator. So the chloride will dissolve, it'll ionize and dissolve, but it's a spectator, it doesn't get involved in the chemistry. So guys, with all of this said, do you see then how this all fits together? Guys, and again, I gave this to you, but this is then the summary of everything that we've said. So when we talk about salts, we understand a salt is just a positive and a negative ion bonded together. So we've got cations on the left, we've got anions across the top. We understand that cations, the metals, can be thought of as coming from bases. We understand that the anions, the nonmetals, can be thought of as coming from acids. And then to figure out what these ions do to water, you've got to figure out if their parents are strong or weak. So, for example, and you've got this in front of you, if we've got a cation that comes from a strong base, and remember we said lithium, rubidium, cesium, potassium, calcium, strontium, those guys. So these guys do not do this. These guys do not attack water. You'll notice, do you have the little line through there? Did it print okay? Guys, that chemistry does not happen. These ions do not attack water, therefore it doesn't affect pH. And again, these are the group 1 and heavy group 2 metal ions. So what about then all the other metals on the periodic table and the positive ions on that are polyatomic, like ammonium? Well, guys, these dudes do attack water. And when they do, they release hydrogen ion, making the solution acidic, so the pH will be less than 7. Then, guys, for the anions, similar logic. If you've got an anion that is worthless from a strong acid, this chemistry doesn't happen. They don't attack water. So again, that would be chloride, nitrate, bisulfate, the ones from the strong acids. Then, guys, the ones from the weak acids do attack water, and as a result, when they attack water, they'll take in a hydrogen, releasing OH, and that would be basic. Good? So now we can bring these ideas together. So let's talk about some examples. So, guys, let's say we've got, I don't know, lithium, potassium, calcium, doesn't matter. So let's talk about some salts. So lithium chloride, potassium nitrate, calcium chloride, any possible combination of these groups of ions. So if we've got, like, say, for example, lithium chloride. Well, if our salt is lithium chloride, what do we know about lithium? Well, lithium comes from lithium hydroxide. Is lithium hydroxide a strong base? Yep. So this is worthless. Where does chloride come from? Hydrochloric acid. Is HCl a strong acid? Yes. So this is worthless. So when they come together into salts such as these examples, the pH is 7 because neither one of them will attack the water. Yep. So neither one of those ions, because they're already identified as being worthless because they're from strong acids and bases, neither one attacks the water. The pH is 7. So now, guys, what about these combinations? What if we take a strong metal cation, that, you know, group 1 heavy, group 2, but then react it with an anion that is from a weak base or from a weak acid? Well, if we do that, these dudes are basic. And when they're basic, they do take in hydrogens from water and form hydroxide. So examples of these salts would be things like this. So sodium from a strong base, fluoride from a weak acid. So, guys, when we have examples like this, like the fluoride will attack water, will form hydroxide. So what will the pH of these solutions be? Above or below 7? They're basic, so they'll be above 7. Is that okay? So now, guys, let's go down here. Now we're talking about the child of a strong acid, the child of a weak base. So we know that the child of the strong acid, which will be the anion, is worthless, but now the positive ion can function as an acid. And when it does, it will take in OH and it will release hydrogen, making these solutions acidic. So for example, if you had aluminum chloride and you dumped aluminum chloride in water, the chloride won't mess around with the water because it comes from HCl, but the aluminum will. And what the aluminum does is it pulls hydroxides off of water, forming aluminum hydroxide, and then the hydrogens make the solution acidic. Is that good? Okay, so now, guys, what about the tie? What about these examples down here where you've got both a positive and a negative ion that mess around with water? Well, guys, to answer this, the pH of the solution will depend upon their relative Kas and Kbs. You guys okay? All right. Try to do this without the table that I gave you. This is actually off of a past AP test. We will be solving this problem again when we start reviewing for the AP test. These are important, but I'll give it to you now. List these following solutions in order of increasing pH. Thank goodness they all have the same molarity. But guys, they did give us this additional bit of information. And, well, yeah, I'll leave it at that. So guys, put these in order of increasing pH. I'll give you 5 minutes, and then that'll leave us 8 minutes to talk about it, and then we're done. So guys, and we're going to talk more about this as we get closer to the AP test. Some of you right now are reading this question, and the first thing that runs through your head is, I have no stinking idea how to figure this out. And that's fair. Understand, you're going to have that thought when you read every question on the AP test. You're going to read this question and your first thought's going to be, what on earth are they even asking me? So guys, understand that that experience isn't foreign. But here's the trick. If you read this question and in your mind you say, I have no idea how to answer this question, and then you go limp, guess what you've just trained yourself to do the first Monday in May? Read a question, not know what to do, and wait for your teacher to show you the answer. Because you need to be training yourself to get over that initial experience of, oh crap, I have no clue. So how you choose to address that is really sort of an individual thing. My response to that is organize. I'm an organizer. And so as soon as I read a question and I'm not sure what to do, I start writing stuff down in columns and I just start organizing stuff. Because I know if I can organize it enough, eventually I'll figure out how to solve it. Because you need to develop a strategy for you that gets you over that initial, oh crap, I'm in trouble response. Because if you just give up and spend the next 5 minutes waiting for me to tell you, you're gonna die when you take the AP test. So guys, do something. Even if you're just drawing circles on the paper, do something. I would tear up the test and run screaming out of the room. So if the molarities were different, the whole game would change, because you would have to icebox all of these. So it would no longer become a short response question. Yeah, and they wouldn't do that to you, but understand this too, Matt. Oh, that's what's wrong. Also, if this substance right here doesn't behave the way that it does, and I'm not going to say more than that, you'd also be in trouble as well because this thing gives off 2 nitrates. We'll talk more about that in a minute. Probably. So guys, there was my attempt at organization. You keep going. No, that's not the answer. That's in the same order they were given. But what I found when I went to solve this is it was hard for me to deal with these things in columns because I wanted to have space to be able to break them apart into their ions, and I like to work down. So what I did when the first time I saw this problem, when I went to solve it, I wrote them horizontally across the paper because it gave me space to work. That was my response when I get stuck and go, crap, I don't know how to solve this. Again, guys, my response is organize. And so as I started to organize these, I wrote them horizontally because it gave me space to work. But no, these are in exactly the same order that they were given in the problem, and that's not the order of the answer. Hey. Oh yeah, the KAs. Yes, increasing. No. Yeah, absolutely. Yeah, no, this is about 2 layers deeper than you would see multiple choice questions. There could be a question on the multiple choice test that says, here's 2 solutions, which one has a higher pH? But no, when you start ordering and ranking things, that's free response. Yeah. No, the free response questions are written to take between like 60 and 75 seconds each. So this would take you much longer than that. What did I say? Oh, I'm sorry, multiple choice. The multiple choice are written to take 60 to 75 seconds. 6. We'll talk about all of this the last day in May, or in March.
Yeah, I was like, oh, you're just gonna leave it to May, huh?
You guys all done? Okay, so this is the way that I solve this question. I don't want to solicit your approaches because there's probably as many approaches as there are people in the room. But guys, based upon the things that we just talked about, the way that I approached this problem was to leverage the idea that not all of these ions are going to interact with water. So if I can eliminate the spectators, the things that are not going to interact with water, I can focus the question that I'm trying to answer. So to do that, I went back to this idea of lineage. So you go to the positive ion, which is in this case, number 1, cobalt. And I asked myself this question. Cobalt hydroxide, is that a strong base? No, so that's going to mess around with water. What about HClO4? Is that a strong acid? Consequently, I can disregard it because it does not mess with water. Rubidium hydroxide. Rubidium, number 37 hydroxide. Is that a strong base? Yeah, so it does not mess around with water. What about HCN? Is that a strong acid? So I can't disregard it. Now I come over here and I say strontium hydroxide, strong base? Yes, disregard it. What about HNO3, strong acid? Also yes, so now I know the pH. Now I go on and KOH, strong base? Yes. So if that's a strong base, it does not attack water. then what about C2H3O2H, or whichever end you put the H on? It's not a strong acid, so I know that that will mess around with water. So then what I did is I added charges. This is positive, this is negative, this is negative. And then I ask myself, how do positive things interact with water different than negative things? Well, positive things, when they interact with water, when a positive thing, and I'll scratch it down if you can't see what I'm thinking about, if I have something like cobalt, which is positive, when it interacts with water, it will take in an OH. And I don't even care about writing the formula properly. That's not right, but it doesn't matter. If it takes in OH, then it's going to leave me hydrogens. So what do I know the pH of that solution will be relative to 7? Lower. So this is going to be less than 7, and I like arrows because the alligators don't help me much. I like arrows to show above and below. Then guys, we now end up with a tiebreaker because now we've got 2 negative ions, and we understand that they're both negative, so they will both interact with water similarly. So now we need to figure out, because we're trying to order these, we need to figure out which one of these is going to be better at doing what it will do to water. So generically, some substance X, when it interacts with water, is going to take in a hydrogen, and it's going to form XH, and then it'll form hydroxide. So whatever this X is going to be functioning as a base. So I now know that both of these solutions are going to be above 7. The question is, which one will be more above 7? And did you notice this little evil trick? What they gave you on the test was the Ka values for the conjugate acids of these bases. So they even expected you to take another logical step. So guys, which one is the better acid? The complicated one or the HCN? Which is the better acid? The complicated one. So if the complicated one is the better acid, what do you now know about its conjugate base? It will be the least effective base. So this will be least effective as a base. This will be more effective as a base based upon the Ka values of the corresponding acids. Did that logic step make sense? So now we can piece these together because we know that both of these will be greater than 7. The question is, which one will be more greater than 7? And the answer is the one that is the better base, and that would be this one. So that would be more better or higher than 7. This will be greater than 7, but it'll be less than this one because that is a less effective base based upon the idea that it's the more effective acid, its conjugate. So then guys, putting these in order, and these were listed as A, B, C, and D. Our increasing pH, so our lowest pH would be A, then our pH 7 would be C, and then the two that are above 7, D, would be above 7, but then B would be even more above 7. So it would go A, C, D, B. So guys, this is a little taste of what we are going to do starting in March. This is also a taste of why my students do so much better than anybody else is on this test, at least in the district. Guys, the reason is because this is the kind of stuff that we're going to be doing when we start reviewing for the test. We're not just going to go back over chemistry, we're going to go over it in the context of problem solving. And we're going to do a lot of this together. So guys, all of that to say then, this is your homework. Scratch it down, and we'll see you guys on Wednesday, and we'll figure out why some things are acids, some things are bases, some things are alcohols, and some things don't do anything at all.